Now that we have a few probability theorems under our belt, I think we can accomplish a couple things in this video. We can do some examples actually using those theorems, and there is actually an extension to that general addition rule that we gave for two events, A and B. What if you have A, B, and C? What does that rule look like, right? So let's see if we can get all that done in this video. So let's start with some examples. And the first one, I will just give some information about the events, and then we will apply the relevant theorem. So let's say we are given that the probability of A is 0.35. Seems like a reasonable number. And the probability of B is 0.4. And let's say we have one more bit of information. So, and the probability, let's say we know the probability of the intersection A and B is equal to 0.2, right? So that's given, right? Now, let's just put this out there. In a particular problem, you might not be given these probabilities explicitly. You might be given information from which you can infer these values, so like there might be a context, there might be a story, but let's just look at this one where the information is given straight out, right? Now, before we look at what we're asked to find, I want to use this opportunity to show you that we can represent these abstract numbers and symbols on a Venn diagram, right? That's one of the reasons why Venn diagrams are useful. Anything visual that just kind of puts everything right in front of you, it's often a benefit to have something like that when you're problem solving, right? So let's see if we can have set up a Venn diagram to represent this scenario. So we look at the information that's given, and we can see that two sets here, right? We have information about two of these sets, two of these events. So we need the general two-set case for a Venn diagram, which looks like that. And as usual, let's call that one A, that one B. And now what I'm going to do, when we were doing this previously, we just kind of shaded certain regions and talked about elements that are here or not here, things like that. And the space didn't really represent much more than just, okay, some arbitrary set of elements. Now what we can do is essentially label this Venn diagram in such a way that the numbers that we use will represent the probability of being in that particular portion, right? In other words, we're not just going to shade it, we're going to figure out what number needs to go just in that region, and what number needs to go just in that region, and here, and then outside. Once you do that, pretty much any question I could ask you, any sort of combination with of these events or their complements, you could just look at the Venn diagram and identify the correct value or values, right? Okay, so let's see how it goes. And the key to the Venn diagram is starting in the region where you have the most overlap, right? Well, in two cases, in a two event situation, that would just be this, right? And we know what this symbolically means in set theory. It's the intersection. And we're told that the probability of the intersection is 0.2. So that's where the 0.2 would go, right? It would be in the portion of these two circles that overlap, right? And then the general principle is now you work from the inside out until you get to, the region that's not inside any circle, right? So it won't take a lot of work when you have the 2 event case, but later on, when we look at the 3 event case, yes, we'll have more regions to fill in, right? But the process is pretty much the same. All right, so what are we going to do? So let's figure out what goes in the part that's just A or only A. Well, if we think about it, all of A has to encompass a 0.35 probability. So that means in total, the entire circle of A must have a probability of 0.35. We already have a 0.2 here, so the part that's just A is going to be the difference between 0.35 and 0.2. So in other words, whatever number I put in just this region, it has to sum up to this probability, right? That's actually one of our axioms, right? We have the 2, remember these are 2 disjoint regions, this one and this one. And this probability is saying that those 2 must add up to 0.35. So what's out here must be, so let me see if I can write down the actual operation. Oh, that's not a 0. So this is 0.35 minus the 0.2 here, and then that will give us 0.15. All right. So so I just wanted to write the steps there, but what I'm going to do, obviously this looks messy, it can be confusing. So I'm going to erase the work that I just did and just label it as the 0.15, and then again repeat why it's 0.15, right? Right, really useful to be able to take these numbers and put them in a Venn diagram, right? So the portion that's just A, and now remember we have symbolic ways of representing this, right? So when we get to questions, you'll see all those symbols, you see the complements, you'll see the intersections, but once you have the notion of what operation represents what region in your Venn diagram, you'll be able just to pick out the number, right? As far as what goes in B, now let's see. B, the entire circle, has a total probability of 0.4. We already have half of that here in 0.2, so the other 0.2 has to be in just the B part alone. All right. And then finally, so in the 2 event or 2 set case, you have 4 regions. We have 3 of them labeled. And this is where we get to use the probability of the entire sample space is equal to 1. So what goes outside, right? So what is in neither of the circles is going to be 1 minus 0.15 minus 0.2 minus 0.2. So in other words, what's inside all the circles is 0.55. So the difference, to make sure that everything adds up to 1, I have to have a 0.45 outside, right? And this is our complete Venn diagram. And then once I have this, now let's see how simple it is to write down literally any combination of these 2 we can find, right? Now, what I will do as we, and I have several parts here that we're going to present, we will use some of the basic theorems that we established in the previous video, and then also we will make use of the Venn diagram. So we don't always have to use the Venn diagram, we don't always have to use the theorems, but use them in a way that you use the most efficient approach for a given problem. So for instance, here's one thing that could be asked, right? And this is a very, it's a simple calculation, but I can't tell you how much using the complement approach can simplify your work? Well, we proved a result previously that said the probability of the complement of A is 1 minus the probability of A, right? Either an event is going to occur or not occur. So in this case, the probability that A does not occur is 1 minus 0.35, which is 0.65. I have no problem, for instance, if you are, submitting written work to write this as 65%. That's completely fine with me. Systems like Mobius, however, might not like the percent sign, so we're going to stick to the decimal, right? As far as using a system like that. Now, here's a way you can check your work. Let's add up all the blue numbers that are outside the circle A, because that's what this is, right? Not A means that you have to be outside of set A. You're not in A. So the values that are outside of the A circle, right? We have 0.2 here, and then we had a 0.45 here. Add those together, and lo and behold, you get the 0.65, right? So there I just showed you one way using the theorem, and the other way just looking at the Venn diagram. All right, let's look at another one. So let's say part B wants us to find the probability of the union. So A union B. Well, we proved a theorem for this as well. And this is what the theorem says. It's the probability of A, probability of B, minus the probability of the intersection. So all these values are given. I mean, if this was the only thing that was asked in this question, I wouldn't really spend the time to draw the Venn diagram unless you really like the Venn diagram. And so the probability of A, I know I just scrolled up, but I'll write it down, 0.35. The probability of B, 0.4, and then minus the probability of the intersection, and the intersection has a probability of 0.2. So what is this? So this is 0.75 minus 0.2, so that's 0.55. How could we look at this Venn diagram and come up with the same value? Well, think about it. A union B is everything in A or B or both. So that means now add up all the blue values in both circles. 0.15 times 0.2 is 0.35, plus another 0.2 is 0.55. So if you add these three values up, right, on these three values lie in the region that's defined by the union, that gives you the probability of the union. All right. Okay, so let me try and let me scroll just a little bit here, maybe a little bit over, there we go. Oh, wait, no, there we go. I want to keep the Venn diagram there and then do enough so that we have space that we can write some more. In fact, let me start up here. So let's say part C. Let's say I want now the probability of A intersect B complement. Right? We've done all the work for this. A intersect B complement is everything inside A but not inside B. So it's just the 0.15 here. Another way of saying this, and which we did when we did those conversions between verbal and symbolic and graphical, another way of saying this is the probability of only A. Right? Well, only A is again this region, so that probability, well, both of these, it's the same, is 0.15. Right? Let's see if we can squeeze another one in there. Part D. What is the probability? Let's do A complement intersect B complement. So in words, remember what this is: not A and not B. So that means you'd have to be outside of, let's see, both circles, right? So you'd have to be outside of both circles, and that's where the 0.45 comes in, right? And you might say, well, is that really true? And in fact it is, because let me rewrite this probability here so you can see it. Using the De Morgan's law, we know that that is the same as the complement of the union, right? That's what this is. So we know that the probability of the union is 0.55. So that means the probability of the complement of the union will be 1 minus this, which is exactly 0.45, right? I mean, there's so many ways you can approach these probabilities, right? And hopefully you're starting to see how they all relate, right? So again, I think we haven't done all the possible combinations, but all the other ones are very similar. Like the probability of B complement will be 1 minus the probability of B. If I did the probability of A complement intersect B, that would be only B, and that would be 0.2. So there's not much, if I can switch the role of A and B, but we pretty much covered all the things that could be asked in a question like this, right? The only additional piece to something like this is when it's not given to you like in symbolically like this, but it might be given to you verbally. So then you'll have to translate it into a Venn diagram. In fact, a good thing to try is just that. So let's look at an example that's a little bit more on the story problem side. So let's look at number 2. And okay, so I'm going to write down some information. So it says 15% of a population, right? I don't know how true this is known to be blonde, right? Apparently blondes have a lot of fun. And then 25% of the population has blue eyes, right? And then 2% are both, right? So 2% of this population is blonde and has blue eyes. And then the question is, if we randomly choose one person from this population, so here's our experiment. Randomly choose one person, just one, right? What is the probability that you choose a person who is not blonde and does not have blue eyes? So what is the probability? So what is the probability that the person let's just say is neither blonde and is neither blue-eyed, right? So is neither. Right? Believe it or not, this question is exactly like the one of the parts that we just did, right? It's exactly the same. And let me show you by setting up the Venn diagram. So So let's go ahead and define our sets. Now, these are both properties that start with the letter B, so it's not going to really make much sense, but I'm going to call this event A. So if the person is blonde, that's event A. If the person has blue eyes, that's event B. All right, so then let's do our Venn diagram. And it's like this. So A, B. So let's see if, again, we can sort of parse out the information and put the appropriate values in the correct region. So 2% is blonde and has blue eyes. So the and there, that's the intersection. So that 2%, and I'll write it as a decimal, that will go in here. So 0.02. My circle is a little too small. See how big I can make this. That should be a little bit better, right? Right, so 2% as a decimal is 0.02, and that goes there, right? Then it says 15% of this population is blonde. So that means my A circle should total 0.15. I already have 0.02 accounted for right here, so that leaves a remainder of 0.13. That would go there, right? And keep going. 25% of the population has blue eyes. So again, the B circle has to total 0.25. Again, we've already accounted for 0.02 of those, so what remains is 0.23, right? And then if we add up these three blue values and subtract that sum from 1, right? So if we do this, 1 minus 0.13 plus 0.02 plus 0.23, like that, that's going to give me how much is left outside of all the all the circles, right? So inside our rectangle, but outside those two circles. So what do we have here? So this is 0.15 and then 0.38. So there we go. And then subtract that from 1, so that leaves 0.62. So that's outside. And that's actually the answer to our question, because it says, what is the probability that the person is neither? Neither is saying, yeah, they're not a blonde, right? And they don't have blue eyes. Well, based on the numbers, right, we can say that's 62% of that particular population. So let's write that down in our set notation. So the probability that the person is neither, there are two ways you can write that down. You could say the person is not blonde and not blue-eyed. Or you could say it is neither blonde nor blue-eyed, right? And again, this relationship right here is our De Morgan's law or properties, right? But however you want to do it, even if you want to just write it out in words to say that the probability that the person is neither is our 62%, right? So this is the type of question where, again, it's not a matter of just always plugging into formulas, but taking something that's more contextual, that has a story, extract the relevant information, see how it relates to sets, see how it relates to set operations, and then now throw probability in the mix with our theorems and properties to identify what exactly is required, right? Because as I said, being able to do this you are able to tackle any problem, right? Honestly, any problem with two sets, this is your approach, right? Now, what if you have three sets? So things get a little bit messier. So what we're going to do to end this video is to give you the general uh, addition rule for for a three set scenario, right? So, and I'm not going to prove this. It's very lengthy because it's slightly more complicated than the two event case. But I'll give the formula, and then obviously later on we will work on examples. So let A, B, and C be subsets of some sample space, right? So these are the sample space, or this is the sample space. And remember that when you say a subset of the sample space, you're referring to an event, right? It's one of the things that have to happen. So let me, again, we know what the Venn diagram will look like. And obviously there are lots more regions here, but you got A, you got B, you got C. So what the theorem that I'm about to write down, it's going to give you the relationship between the probability of the union of these three, right, with with this part where they all three overlap, and then the parts where two overlap, like here and here and here, and then the parts where there is no overlap, so like here. So essentially what it does, it kind of breaks up the whole, right, what's inside all three circles, into all of these little pieces, right? So let's write it down. So here is the theorem. Right? And it basically says this, and there is a pattern. So the probability of A union B union C can be written like this. It's kind of a long expression. So it's the probability of A plus the probability of B plus the probability of C, right? So you add up the probability of all three events first, right? Then what we're going to do is minus, so there's a minus, just like how there's a minus in the formula for the two event case, right? The general addition rule. And then what you're going to subtract is you're going to subtract each of the pairwise intersections, right? So A intersect B, A intersect C, and then B intersect C. So you find the probabilities of all of those, or in many cases that information will be given, right? And then the last thing you do is add back in the probability of the intersection of all three, like that, right? And this is the result if you're now talking about three events, right? And what we will do, either in future videos or through workbooks and so forth, we will do examples of this. But I just wanted to show you that the case for the probability of A union B can be extended to the probability of A union B union C. In fact, this can be extended even further. It just gets really, really long the more events you have, right? So maybe if you're nice, I'll show you what that formula looks like, right? So I'll see you in the future.